Yeah.
Sorry, I forgot the mic. Alright, so to get started, part 8, question 1 says that we have a bent bar that's on a sort of hinge, and we're assuming that we're ignoring friction because they didn't say anything about that, and we're given that the angular speed of the bent bar about that point, which I labeled point A, is 0.3 radians per second, and we're also given the height and length of each bend of the bar. So I'll write this on the board. Hold on. Okay. So this is what we're given, and I'm calling this point A, and we're trying to find the linear velocity at point B. And so height h is 0.3, L is 0.7 meters, both of them. So the approach that I used for this problem is relatively straightforward. We have the formula that velocity at a point is the initial velocity or linear velocity plus omega, which is the angular velocity cross r from Q to P. And because we're only asked to find the magnitude
The first velocity on the right-hand side is the velocity of Q.
Oh, sorry.
No, that's fine. That is P. The first one on the right-hand side is that of Q.
Right, okay.
It's not called the initial velocity.
Right, yeah. So
and all of them are with respect to a particular reference frame. So you have to first draw that reference frame, and on the left-hand side put as a pre-superscript that name of that reference frame.
So
introduce a reference frame first.
Right, so the reference frame, I guess, would be the bar as a whole.
Yeah, that could be one reference frame, but these velocities, if you take with respect to that, then Vp, Vq will all become 0. Omega will also become 0.
Right,
that equation will just become 0 equal to 0.
So the reference frame, I guess, would be point B. The reference frame is point B, and we're finding it relative to point A in this case?
No, see, both B and A are parts of the same rigid body, right?
Yes.
So whatever coordinate system you use, if you fix the frame to this, then all velocities will be 0 with respect to that. Unless A is moving around on that or B is moving around on that, which they are not, right?
Right.
So you need a frame which is different from the body, a separate frame.
Okay.
He's referring to inertial frame of reference.
Right, you understand,
So,
right? So, like
right,
for
so
all
it would be
things that we've been introducing a coordinate system. So that's the frame with respect to which all these velocities are defined.
Okay.
Right. So
So
if I may.
Yeah.
So this has to be with respect to a particular inertial frame, or it could be an earth fixed frame, in which case it would be E. Similarly, this velocity is also with respect to that frame. This is of this body, if I may call it, let's say B. Then it's the angular velocity of B with respect to I. Okay.
Okay.
So then you will have.
So is the inertial
Frame
frame,
of
of
reference.
reference what we're finding the velocity relative to?
Exactly.
Okay, so then it
So
would be
depending
A.
upon which frame you choose, the actual values of these will be different, these three.
Okay.
This will be the same, okay? So it doesn't matter. But because it's just going from one point to another point on this, you can express it in various coordinate system, but it's fine. The vector will not change, its magnitude and direction will not change. But these three values will itself change, both magnitude and direction, depending upon which frame you use.
Okay.
So when you're talking of RQP, doesn't matter, but for all these three, the frame I is very important.
Okay. So the inertial reference frame would be the hinge on which the bar moves. So there. So finding R.
No,
since we're-
so let me clarify. By frame, we mean any other rigid body, which in this case is the
would
Earth.
be the hinge.
Yeah. So
of the
this
Earth.
is already this entire thing that you have drawn, this L, is a rigid body, which is what we are calling as B. So we don't need any further boxes there.
Okay.
Because even if you had another frame there, that would move along with B. However B rotates, that will also
Well,
rotate. However,
the hinge is a separate body, correct?
the hinge, no, let's not complicate things, because the hinge has a pin, right? So that pin is fixed compared to I. So you can think of I as being at that hinge also. There's no problem with that. Okay.
Okay.
But essentially you're saying that this whole thing is a rigid body. Okay. So A is of course not moving at all, right?
Yeah,
Because
it's not.
it is hinged. Only thing, there's a rotation about A.
Okay.
Right? So by frame we mean something which is like a massless rigid body, or it could have a mass, doesn't matter. Okay. But essentially something else with respect to which you are comparing the motion of B.
Okay.
Okay. So which is what I've drawn here already. So you don't need any further frames. For this
Yeah.
simple problem, there's one
just
body whose motion
the
you're trying to
surroundings,
determine in terms of one point with respect to the other. And that motion has to be with respect to another frame. And that frame also you have, I have already put it there. So this is all that you need, these two frames.
Okay.
So you understand the concept of frame now? Frame just means another rigid body. It could be the earth.
Yeah.
Okay, it could be the sun,
So
it could
not
be whatever.
in the system.
Exactly,
basically.
exactly. So you as an observer, you are standing in this frame and observing what is happening there. Then only you can start using an equation like that.
All right.
Okay. Otherwise, as I said, if you're, let's say you are taking a joyride on this, you're sitting on this, then this will go to 0, this will go to 0, this will go to 0. You'll just be saying 0 equal to 0. You cannot actually use this equation.
Okay.
That's why you need a frame which is separate from B, which is what we call as I here.
Okay. So this equation, if you apply to this system, you'll find that, well, this is VB equals VA plus omega cross RAB. And RAB is this vector right here. And because we're given that we only have to find the magnitude of the linear velocity, we are given the radial velocity, so we can basically turn this into magnitudes and deal only with the magnitudes to save ourselves the trouble of doing a cross product here. And also we aren't given a vector quantity anyways, so we wouldn't be able to. So essentially the magnitude of VB equals magnitude of VA plus, well, omega R. That would just be a single quantity. And we also know that this hinge isn't moving, so VA is 0. So that just
The
cancels.
magnitude of a vector is not equal to the sum of the magnitudes of two vectors that it's made of. It's for the whole thing that you will have the magnitudes, not just, right? So,
Right, yeah.
so suppose I have two vectors. If
So
I'm
it
summing them up, I cannot just sum their magnitudes, right?
Yeah.
No, you can't.
What?
You can't do that. It's the entire right-hand side's magnitude that you'd be interested in, which is why it's important that you continue with that vector. So write VA and VB in the coordinate system that we have introduced. So for that I, can you introduce IJK, the inertial frame that I have drawn on the bottom left?
Yeah.
Yeah. Can you introduce, let's put K on the one coming out of the board.
Yeah.
Yeah, I for the horizontal and J for the vertical. Okay. Now you need to write VA, VB and omega in this system. Okay. You have the magnitudes there, but you should also know the direction. Okay. Because all those are vectors,
Yeah.
right? So which direction is VB in, which direction is VA in, which direction is omega in, all these things are important. Okay.
Okay.
So VB of course is something that you don't know because that's what you're going to find out, right?
Yeah.
But you have been given the rest of the things.
Yeah, but VA
right?
is 0. So
Okay.
I guess if I make A do I put A at the origin then?
You can call O, yeah, you can put that. Yeah, sure. You can draw the same ijk at A. You can draw the same 3 axes at A there on top. You can draw at A, you can draw those 3 axes there. Because A is a hinge, it's fixed in
Yeah.
I anyway.
Sorry, this is
Yeah, very good. So call them ijk again. Yeah.
yeah. Well, it's not moving about the k-axis.
Correct.
So it would just be having a radial motion, which is omega, about the origin.
Yeah, omega is about which axis?
It's about the k-axis.
Yeah. So that angular velocity I omega b is now equal to the magnitude omega times k hat.
Okay, yeah. So k hat, okay. So here k hat is 0, 0, 1. And then multiply by 0.3 and you get omega equals 0, 0, 0.3. And the radius is, it's on the ij axis or xy axis, so that would be negative j. Okay, those would be the 2 vectors. And then if you do a cross product on those 2, and then we have to take the magnitude of this whole thing. So first I guess just do a normal cross product. So that's 0i, and then minus well, it's minus negative. And then plus, which is 0k. Okay. So that means 0.21. I think so. 0.21j. I'm pretty sure that's, yeah. So 0.21j hat should be the cross product. And then you multiply that, or no, not multiply. So the magnitude of that is 0.21.
See, how do you take the cross product? You write a determinant, right?
Right,
ijk
yeah.
on the top row,
Yeah,
right?
I did
First
that
row.
in
Yeah.
my head.
Okay. So when you do that, how will I hat term become 0?
Oh, sorry, my bad. It's 0.9. Okay. So then, because we know that the magnitude of VA
How much is
is 0 and the
0.3 times 0.3? Yeah, and what's the sign? Yeah, no, but I'm just trying to trick you. How do you get to the sign of that term?
Well, no, it would be positive.
Why?
Because it's 0 minus negative 0.09.
Yeah. Correct.
Okay. So then finding the magnitude of that is 0.09 squared plus 0.21 squared. And that gives us hold on. Sorry, I didn't do this calculation. It's 0.2285. Yeah, so that's that's the magnitude of the velocity of B.
What is the unit?
In meters per second. And that's because this is given in meters and the omega is given in radians per second. And radians per second times meters is meters per second because radians
Okay.
isn't really a unit.
Does that agree with the answer given?
And okay, so I was gonna go to the applications.
Okay.
I'm not gonna take too long, but
But does the answer agree with the what is given in the question?
yeah, it does.
Yeah. Okay. Sure.
Yeah. Actually, how I originally did this problem is because we're given that it is in magnitudes, there is a different formula that you can use without the vector quantities, and that would just be v equals omega r. And if there is an initial velocity, or if there is a velocity already on the point that you're trying to find, then you would add that on to
So
omega
instead of calling
r.
it initial velocity, you can call it a velocity of a point on the same body, right?
Right, yeah.
So if you know that one point on the body is not moving, with
Then
respect to that, then you can use the magnitude of omega times
Right,
r.
yeah. So that's what I originally did. And the application is that you can basically you turn the polar coordinate, essentially what that's doing is turning a polar coordinate system into a Cartesian system because you're trying to find the relative r, as you can see there. In polar coordinates, the position is r times omega. And so also in polar coordinates, r times theta is position, so then r times omega would be the linear velocity in Cartesian coordinates. So that's one application. And another thing is pendulums, like the one in this problem, are often used for stabilization. So in the Taipei 101, there's actually a pendulum that is mass bearing, so it stops it from, being thrown around in the wind or in earthquakes. So that can kind of be an application of this problem because we are given a system on a hinge, and there's a similar bar system that's used inside the giant ball there. Obviously you can't see it, but there is a mass in there that's being moved around relative to the swinging to reduce the amount of angle change in the building. And another thing is if you do have friction, so this is relatively frictionless, but if you do have friction in the system, then that would kind of be similar to utilizing torque to open a handle, which is also a sort of bent bar. So it's another application of this problem. Yeah.
I really appreciate that you go beyond the question to bring in
Yeah.
a few applications. That's important. for future homeworks, I'd suggest everybody do that. And in particular, if you can find an aerospace example, that will be even better. So just one comment, you mentioned linear velocity v. So as I explained, we would though most books do call it linear velocity, we would prefer to call it translational velocity to avoid the confusion between linear and non-linear. Okay. Sure.
Okay, so I had part A, question 2, and question 3. So we can do question 2 first. In this problem, we're given this sort of setup, and we want to find the angular velocity of bar B2. So I'm just going to redraw the picture here. And there are a couple things that we know about this thing. We know, for instance, that these two supports are placed 10 inches apart. We know that this first beam is 8 inches in length this way, and we know that this beam is 12 inches this way. This is beam 1, this is beam 2, beam 3. And in our points, we have O, A, B, and D. We also know our frame of reference to be, we have this coordinate axes with our I and J. So this is our frame of reference. And the way to sort of go about this is we kind of need to set up a system of equations. We could do that by first trying to solve, also for like our knowns, we also know the translational velocity at A is equal to 96.2 inches per second in the I direction. And using this sort of information, we need to try and solve for the angular velocity of B2 at point B. So the way we can do that is we can first set up, I guess, our first equation being to solve for the translational velocity at point B being equal to the translational velocity at A plus the cross product of the angular velocity of beam B2 and the length between the two. So I guess this vector radius from A to B. So that's our first equation.
Omega is also vector.
Oh, yes. So what we can do is we don't know the angular velocity of B2. That's what we're trying to find. So we want to obtain expressions in terms of that. So we can first solve for the cross product of this omega B2 and the position vector. So I'll just put it here. We know that this, I forgot to include this, but this is in the k direction, this angular velocity. So we can write this.
Once you put k hat, you can remove the underline.
Oh, okay. And for for our position vector from A to B, we know that from the measurements, we're going positive 10 in the I direction and positive 4 in the J direction. So we can put these in here. And then we can find the cross product. So this comes out to negative 4 omega E2 10 omega 2 0. We additionally know the velocity, the translational velocity vector at point A, so we can write that out as being 96.200 plus.
Your I and J might be interchanged there, right? The solution that you got there, the cross product.
Yes, it is. Yes, it is. That is my mistake. I don't know. That is
Correct. Yeah.
Yeah.
It is negative.
Yeah, that's negative. Okay. And that is negative. Okay. Yeah. Okay.
The second one is positive, right?
Yes. Yes. So the expression that we obtain is in total minus okay. So that's the expression we have for VB. We can apply a similar process for the second beam as well, because we still have two unknowns here. So we can set up another expression using the relationship between points C and B. So that equals to plus the angular velocity of beam 3 times the cross product times the position vector of BB. Okay, so now we take this cross product in a similar way. So again, this is in the K direction, so we can put it here. And for the position vector BD, we know that it's going down, going down 12, so 12 in the negative J direction. So we can write as such. And evaluate the cross product of this as well. So we get
Check the sign.
Oh. Okay, yeah. So because we evaluated for BB before, we can plug this expression right back in. So we have the last piece of information we're given in the problem is that the velocity of point D has to be 0. So we know that this vector, the velocity vector, the translational velocity vector, FD, is the 0 vector. So we can write that as 0, 0, 0 is equal to the sum of all of this. Right. And now we can sort of take the components of each vector and treat it as now its own system of equations. We have expression for the I component and the j component, so that can be, and we have two unknowns. So it's a perfect system of equations that we can solve. So we have
12 is omega b3, right?
Oh yes.
On the top also.
Not. Did I? Okay, yeah. Yes, okay. So that is equal to 96. So the question is only asking for omega 2, which is pretty easy because you know from the second equation that omega 2 has to be equal to 0. Well, would it just be equal to the 0 vector?
Yeah,
Or-
it doesn't matter.
Okay. Yeah, so that's problem 2.
Yeah. Okay, good,
Is that
thanks.
good? Okay, I have to do
It
question.
agrees with the answer, right?
Yeah.
Yeah.
I have to do question 3 now. So, okay, now we can do question 3, which is now asking to find the angular velocity of bar B3, and it's giving a slightly different translational velocity at point A. So, I'm just going to do it below here. We can again go through a very similar process. This time we have our VA being equal to 92 inches per second in the I direction. And we're keeping the same frame of reference. And all parts of the figure staying the same, so it works out. So, set up our first equation, the relationship between A and B. We can write this as, again, it's like basically the exact same formula in the k direction with the cross product with the position vector AB. And because I already did the cross product there and it's the exact same, I'm not going to do it again. But this time our translational velocity at A is a little different, so we can just write that down. Right. Okay. We can also do, I was a little bit confused about this because I wasn't sure if we could make the same assumption about the translational velocity at point D being 0 as well.
Yeah.
Is that
Yeah, because see, whenever you say velocity, it's with respect to a frame, right?
Yes.
In this case, it's the frame I,
Yes.
right? And whether it is D or A, both are, O, what you call that? O, right?
Yes,
Yeah.
O.
So D and O are both hinged, right? So
Yes.
if it's hinged, then essentially it's fixed in I. If it's fixed in I, then its velocity in I is equal to 0. So IVO is 0, IVD is also 0.
Okay. That works because I made that assumption, but it's good that it actually is not an assumption. Okay, so now we can do the same thing with the
It's an
translational
assumption that the hinge is perfect. things in
I
reality
see.
may not be perfect, right? If there's a wear in the hinge,
I
then
see
it might have a
Yeah.
small motion.
Right. So this is very similar expression. And again, we have our expression for the tangent for the translational velocity at point B. So you can put that back in. This added the cross product between the angular velocity of B, should be 3, and BD, sorry. Yeah. Wait, no, that was... Okay, yeah, here, okay. What was that? That was 12 omega B3. Okay. Yeah, so we can again combine all of those expressions. And then once again we have, because we're saying that this is the zero vector, due to assuming that it is a perfect hinge, we then once again have our same sort of system of equations with our I component and our j component. From this equation, again, we can say that the angular velocity of beam 2 is equal to the zero vector. So, let's go 0. So in this term, this will come out. So we then get that 0I is equal to 92 minus, or plus 12 omega B3. And so if we solve for omega B3, you get -7.67 in the k direction, radians per second.
Good job. Butterfly.
Alright, so for this problem...
Andrew, can you please use the microphone? You can probably use the magnet to put it on your t-shirt if you...
The mag? Oh. Okay. So I began by drawing, I'm using a Cartesian coordinate plane. So I have my x, which is dependent or has a unit vector of I hat, and then y chooses a j hat, and then I chose my z positive to be outward from the page. That's dependent on, or has a unit vector of k hat, and then I set it to be an inertial reference frame. And so we want to find the velocity at point P. And so we need to use this equation where the velocity at a point P is related to the velocity at a point Q, where Q is on the same rigid body as P, by adding omega cross the position vector between the 2 points. And then so I set up the problem by drawing a little diagram to represent some of the values given in the problem a little bit easier. So I'll draw that real quickly. Okay, maybe it's not too pretty, but okay. And then this is just kind of to like ease the clutter a little bit. So I'll set this as point A, this as point B, this is point C, and then this as point P as defined in the problem. And then we're given that this length is 0.4 meters. And then we're given this total length is 0.5 meters, but we only really need the distance between the 2 points. That's 0.3 meters. And then we're given that the circle has a radius of 1, so the distance between these 2 points is 0.1 meters. And let's see. And then so I define the origin of this system to be at point A. That's just like a choice I made. So I have A to be have a coordinate of 0, 0, 0. B has a coordinate of negative 0.4, 0, 0. C has a coordinate of negative 0.4, negative 0.3, 0. And then P has a coordinate of negative 0.3, negative 0.3, 0. And these are important because we'll have to use the difference between these points to find the position vectors, or the difference in position vectors. And then, so first we begin finding the velocity of point B by substituting the values into the equation where we have...
Can you put arrowheads over V as well?
Oh, yes.
Yeah.
And so we have the velocity at point A plus omega 1 cross R, and that would be AB. And then so